everyone. My name is XinChen. I'm a data scientist of Ernst based out of Boston, American office. I have been working in the AML field for about 5 years post my PhD graduation, and my responsibility within EY basically leverage AML to helping to solve the problem of the banking client, to help them to build AML service. So the work I'm presenting today is one of our work, basically the sequential recommendation model to predict what the next best transaction would be for the user. In this presentation, I will first give an introduction about the recommendation system and also talk about why we want to build the sequential recommendation models and our proposed approach. And also I will talk about the data we're using for model training and how we prepare the data to train the model, as well as the model results. And then I will briefly introduce the machine learning architecture we built to host our sequential models, as well as related service to deliver the location aware of offers for the user's next best transaction. And then I will conclude my presentation. So the recommendation system, actually, I think most of people are familiar with it. Actually, we're experiencing it every day in our daily life. It suggests the relevant items to the user based on their past experience, their past purchase views, and their preference. Like when we're shopping online from Amazon, from eBay, or from other online e-commerce, or we view the watch the movies video from streaming platform, those kind of apps or the platform also recommended the relevant items, or say the items that the user will be mostly likely to either purchase or view. It helps the user to narrow down the options to purchase to view by marketing attractive items and thereby enhancing the user's experience and boost the sales. It has been reported that, say, the recommendation system can help to increase the click-through rate by up to 30% and lift adoptions and conversion rate by 2 to 5%. Therefore, the better, or say the more accurate the recommendation model is, the higher click-through rate, which also means the more sales revenues. And nowadays, we're noticed that for the banking, for most of the banking apps, it provides the features, basically provide the offers with either cash reward or say discount when the user shopping at a certain merchant. But we also noted that those offer recommendations are mostly static. Basically, it's not personalized. Most of people may receive the same offer recommendations, and also most of the offer recommendations is not location aware. So how to build the recommendation models to provide a personalized location aware of offer recommendation is the main problem we're trying to solve here. So for the recommendation models, there are multiple ways, or say technicals, to implement it. For the most conventional ways, the collaborative filtering or content-based filtering would be two most popular ways to build the recommendation models. So for those conventional recommendation models, those techniques, they kind of assume the user's profile or the items attributes are static. It's not considering about the preference change of the user, and it's hard to capture the temporary dynamic of the user's preference and the items attributes. But in the real world scenario, the user's preference is usually changing over time. Like the user's preference on the certain brand or the style or their affordability always change over time. So, and Secondly, in the real-time scenario, the user-item interaction are usually sequentially dependent. Like in this diagram, one of the user book a flight, book a taxi, and book a hotel in the other town. Most likely, the user is travel out of town, and the next transaction probably would be shopping at the some recommended the restaurants out of town. That means the user's next transaction, or say the next actions, is usually dependent on the few of last transactions the user have made. And the recommendations often are only relevant if they're attainable to user. That means if it's better to recommend the user to the local merchant instead of some other merchant out of town. And also the price should be reasonable so that the user will be more likely to accept the offer. So this is, given this scenario, it's challenging for a conventional recommendation system to capture those kind of sequential dependencies and dynamic preference. Therefore, the sequential recommendation model is very critical to deal with those kind of scenario. And so the question, to be more specific, what we're trying to solve is, say, given the user's past transaction sequence, what the next transaction would be. And to be more specific, we want to, if we know the user's past a few transactions, what the industry code or what the industry code and the transaction amount for the user's next most likely transaction. That means if the user would like to make a purchase at the restaurant, or they want to book a flight, or they want to book a taxi, so on and so forth, we want to know what the industry for the next transaction, as well as the transaction amount, whether the user, that is how much money the user is willing to pay for the next transaction. Given those two informations, it's easier for us to filter out the right offers to suggest to the users. And in this case, we proposed a model called sequential recommendation model for next best transaction, SEQ and BT, to solve those problems. So the sequential, our sequential recommendation model basically composed of 3 key deep learning models. One is the BERT model, the pre-trained BERT model. We use it to deal with the text data inside of the transaction data. And then the second deep learning model we applied is auto-encoder model. Basically, we use it to encoding the transactions. That is to say, each transaction, every transaction will be encoded into a dense vectors to represent that transactions. And then the third deep learning model we use here is the GRU, the gated recurrent unit sequential model, to take the sequence of the transaction as input and then predict the transaction encoding for the next transactions. And then the predicted transaction encodings will be decoded back to the human interpretable features like the transaction amount and the industry code. I will go to detail for each component of this model in the following slides. But this just give the high level about our proposed model. So before I go to this session, probably I can give a example about the transaction dataset we're using. We're using credit card transaction dataset for our model training and the prediction. Here is the example of the credit card transaction data. It contains the information about the card number, which is hashed and encrypted, and the transaction date, when the transaction happened, the transaction sequence number. Those two columns is actually used to order the transactions into the temporary order. and the amount, transaction amount, supply number, which is the identifier for the merchant where the transactions happen. The MCC or SIC numbers is MCC number is a merchant category. Those is like a 3 or 4 digits number to indicate which merchant category those merchant belongs to. The SIC number, the industry code, which is the main, I would say the target we want to predict, the industry code for the next transactions. And the SIC string, which this is a text string to describe what this industry code means. For example, here is the example, the SIC code is 5814. It indicates this merchant belongs to a fast food restaurant. So this is an example about the credit card transaction data set we're using. And go back to the detail about the models. So the pre-trained model, the pre-trained BERT model is used to embedding the SIC descriptions to convert this text description to the numerical vector used as a feature for the transaction encodings. So we gathered the text description for all the SIC code presented in our transaction dataset, which is about over 200 unique SIC code. And then we run the pre-BERT model to generate the SIC embedding for all the SIC descriptions and save it into the feature store. Those information will be used not only in the features of the input, but also the reference table. When we predict the SIC embedding for the next transactions, we will compare with this reference table to calculate the similarity between the predicted SIC embeddings with the SIC embedding libraries to get the industry code for the user's next most likely transaction. The autoencoder is another model that we used to encoding the transaction. That means for each transaction, we will generate the lower dimension, or say the dense representation for that transaction. So the autoencoder model is something like this. It's a symmetric model that the input would be aggregated transaction features. For example, the total number of transactions within the last 7 days, 30 days of this user, and the total transaction amount of this user within the last 30 days. 7 days, for example, those kind of the aggregated transaction features, along with the SIC embeddings. SIC embeddings is like 768 dimension vector. So this concatenated vector will be the input for the autoencoder model. It will first express the input to a lower dimension. We use the 32 dimension you can see in this bottleneck layer. And then it will reconstruct it to the dimension same as the input. And the difference between the original input and the reconstructed output will be reduced or minimized during the model training process. And then the encoder part, we will use the encoder part to generate the transaction encodings for each transaction. And then the decoder part will be used, the decoder part will be used at the end of the model to decode the predictions back to the human interpretable features. I will show the end-to-end pipeline in the next couple of slides. And as I just describe the sample we're using. So basically in our data set for one user, right, they may make multiple transactions. So we basically slide the transaction, the user's transaction sequence. And so for example, if we want to take the user's last 5 transactions as sequence. And when we prepare the training data, we will group the 5 transactions as the training data, and then the transactions and the next transaction would be target. And then we move the window over the sequence of the transaction to get more training observations for the same customer. That is how we prepare for the training data. And then in this diagram, basically, we show the end-to-end process from the original transaction data. And like this, we have the card numbers, the transaction date, the SIC descriptions, and transaction amount, and as well as others. And we first do the generated the aggregated features, the customer in industry features, and as well as in embedding, generated the SIC embeddings using the BERT model. And then for each transactions will be go through the transaction encoder to generate the transaction level encodings for each transaction. And then we group the transaction encodings by account to get the transaction encoding sequence for each account. And then we group the transaction encoding sequence by the fixed windows to generate the training data, right? And then we pass the sequence of the user's transaction as input, and then predict the transaction encoding for the next best transactions. And then once we get the transaction encoding for the next best transactions, then we use the decoder part to decode it back to get the SIC embeddings and the aggregated transaction features. And then the predicted SIC embeddings will be, the distance between the predicted SIC embeddings with our SIC embedding libraries will be calculated to rank the SIC code so that we can get the most likely SIC code for the next transactions. This is the end-to-end flow for our sequential model. And in terms of model results, we use the mean average position at a cut point K and the recall at the cut point K as the evaluation metrics for prediction on the industry code. And as well as we are predicting the transaction amount, basically how much money the user is willing to pay for their next transaction. We use the mean average error to evaluate the performance of the prediction on transaction amount. So the best result we're getting is like the mean average position for the next 1 transactions in predicting the industry category. We got the 47%, which is very predicent, which very align with the maximum MIP at 1. This metrics reported right now. And also we compare the performance of our SEQ and BT model with 2 baseline models. One is the attention-based recommendation models. One is the GRU-based recommendation models. And we see our sequential model actually outperform the other 2 baseline models very much. We think the reason of the outperformance is due to we considering the extra item context like SIC embeddings and as well as the temporary information. So here I just give an example of the output. So for example, if a account made a purchase, like they have multiple Uber transactions and also go to the restaurants and also the automobile parking. This is the transaction sequence, 5 previous transaction sequence for a user. And with the model, the output is something like this. We predicted the next transactions, the user will be more likely to go to the restaurant and spend the $20 for the next transactions. We are actually, for the ground truth value for this user, the user did go to the restaurants but spend like $30 for the next transaction. So this example shows we can get the target industry code correct. So an offer could have been generated and the successful target. With this information, the next question we ask is say, how we can deliver the insights from our sequential models to the user at the right moment, because the model predict, okay, the user will going to restaurant spend about $20. How we can deliver the offer to the user at the right time, at the right moment. Then I want to introduce the machine learning architecture we use to embed our recommendations into offer-based journey. And this is a diagram of the UI Nexus. UI Nexus is one of UI product. It's a cloud ready and event-driven platform. It's designed to deliver the user personalized experience at the right time, at the right channel. And from this diagram, actually, you can see it's built with several like ready to go service. The underlying component enable the Nexus platform is called event engine, which translate incoming signals into directed cyclic graph, the event map we call. Depends on the specific context, these events are used to kick off either ETL pipeline or feature generation pipeline or a scoring procedure like our SEQ-MBT framework or customer nudges. Then the insight store is used to facilitate model execution and support the feature store lookup, communicate with downstream service to kind of deliver the insights to the downstream service. And then lastly, here is the customer experience manager. This CEM module is responsible for deciding which message to send via which channel at when to deliver those kind of information. So this is basically the idea about the UI Nexus platform, which we use to embedding our recommendation models to deliver the offer based to deliver the offer to the users. And that is to say, as soon as the customer enters qualified locations, we can instantaneously update his or her available offers, while the offers themselves are identified by our SEQ-MBT models and some of other related service. And then specific delivery and the notification preference are handled by CEM. So this is a high-level idea about how we use this platform to deliver the offers to the user at the right moment. And then to conclude our work or semi-presentations, we propose the SEQ-MBT model, which can take the past transaction experience, can take the user's past transactions as input and then predict the industry category and transaction amount for the user's next most likely transaction. And from the model result, we can see our model actually predicted the can give a very decent output for the next best, for the next transactions prediction. And also I presented the high level architecture about the UI Nexus product, how it can deliver the predictions to end user. And in the future, okay, so right now the SEQ-MBT model is kind of specific designed for the credit card transaction dataset. In the future, we anticipate to generate or say leverage SEQ-MBT model to other domain of to other data domain using not only just the offers space, but also some other experience interaction management or some other applications as well. And Yeah, so for more details about the EY Nexus for banking solution, here is the website you can take a reference to. And in case you're interested in this EY Nexus product or the SEQMBT model, I just attach my email address here, and I will post here for any questions.